people coming in. This is cool. Hi. Who said hi to me? Someone. I'll just wave at you all. Just saying, we've got like a 2-hour tutorial. Why not sit next to each other and make a brand new friend? Just an idea. Then again, it's Linux, so. Yeah. So everyone's obviously here for a reason. We're here for Andrew's talk, tutorial even. There is going to be a break in the middle. If you need to go to the bathroom, ask questions, that sort of thing. That will be like halfway through and you can do whatever you like. So this is Andrew McDonald. He seems pretty cool and let's let him start. High five.
What it says on the screen. There's a fortune cookies feature that comes up when you first run the program, and I saw a few interesting and unexpected words pop up, so I don't want to be responsible for violating the code of conduct. So I do believe, and I'm thankful, a bug report has actually been submitted, so maybe they'll sort that out for us. So today, I'm going to be introducing a piece of software called Radare 2. I don't actually know how it's correctly pronounced, so if you are in the project and watch this, I apologise. So we're going to have an introduction and work through how to use the software. I'm going to have a break partway through for general questions because this is a tutorial, so I do encourage some interactivity, although I want to try and keep things moving a bit, so we'll play it a bit by ear. After that, I'll be doing a bit of a brief presentation on MIPS architecture because that's something you find in a lot of embedded devices, and it has a few quirks compared to some other systems on how you might have to go about disassembling the software. If I get a bit of time, I'll just do a quick demo of how to unpack a firmware if you actually find something to pull it out of. And if you're following along, you don't have to use the examples I've got. If you've got other numbers or another binary you want to have a play with, go for it, because we're here to learn. I discovered this software myself only about 6 months ago and thought it was so awesome I had to share it with people, so that's why I've ended up here. And I think that's a duplicate slide. So I'm just going to tell a quick story. This is a gadget which about 6 months ago I was wandering around and I went into Cash Converters, which in Australia is a second-hand recycling shop. In the bit next to all the iPhones and all the rest of it, they have USB modems and other things, and this was in a little black box, and it was one of those USB-powered Wi-Fi repeater things. It's a generation older than what you get now, and I dickered them down from $15 to $10 and took it home because I thought, well, I'll pull it apart and see if I can run Linux on it. It turns out it does actually run a form of Linux, but it's not supported by OpenWRT, and it was not really supportable for various reasons, which I won't go into, but I had trouble actually getting into it in the first place. You can see there's like pins I've soldered in, so if you ever want to try this, most devices you buy, when you pull them apart, there will be 4 little pins, and you can Google that to get pictures on the internet where you can solder in a connector and connect a USB serial port and actually get to the device without having to go through the web firmware. And I wanted to boot my own Linux because I managed to get an OpenWRT image and attempt to boot it, but I couldn't upload it in there. I could get into their Linux using the USB, and I was able to copy it off onto my computer to look at it, but I couldn't get one back in there because I couldn't understand the bootloader. It wasn't U-boot like most of these devices have. And so that led me down this path of how do I reverse engineer this bootloader to get into it, and that's how I discovered Radare 2. And it turned out that this bootloader had a hidden mode that they weren't showing in the help, where you could download firmware across the serial port using something called Y-modem, which was used 20 to 30 years ago when we had dial-up modems before the current internet to actually connect to BBS. So that was an interesting journey. So that's what today is about, is finding gadgets and trying to work out what's inside them, for example, and various other reasons. And I need to press that button and do that. That's awesome. So Radare is a reverse engineering framework, or that's what I call it. So it's a piece of software that lets you do a variety of things. You can use it to disassemble program code that's in binary form back to something called assembly language. I'm going to guess that most people here know what that is. It's like the bottom level of instructions you get when you compile a program in C. Now that alone, you can already do that with a program called GNU objdump and other programs, so that's not particularly interesting. But what a reverse engineering framework lets you do is attempt to discover higher level features in the disassembled code. In particular, visually you can see links like jump instructions and function calls. You can use it to script it and try and unravel data structures which you might not get just by looking at a raw assembly. And people use these tools to modify existing software and do something called fuzzing, which is usually used to look for security-related bugs where someone has forgotten to correctly write memory buffering. Is anyone following along with the software that was on the wiki? Was there any issues? Everyone got it sorted? Cool. So why would you want to reverse engineer something? Because it may have slightly dodgy connotations to some people, but there's very good reasons. You might want to have an existing device and you want to make it work with something else. You may have your own. I've come across businesses that have got their own software and they've actually lost the source code to it and they need to work out how to connect to it and get it started again. You might just want to learn how something works. Often some compilers can actually have bugs in the compiler, and sometimes you need to look at the disassembled code of the code they produce to work out why your code doesn't work. And people will use these tools to analyse malware to try and work out how they work and then come up with defences against it. And that pretty much repeats everything I just said, except radare supports all those features. So today's a tutorial, so I'm going to stop talking a bit so much now. One of the things about radare that I found most useful is not just the software itself, but it comes with a suite of ancillary tools that are built in a Unixy type way. So you can do one thing and combine them together in shell scripts if you just want to do parts of an analysis or deal with conversions. So if you're following along, I'm going to switch to the first one. So there's a program called rax2. Whoops, that's the wrong one. And that's used for just doing number conversions. And in its simplest form, you just give it a decimal number and it gives you the hex. You can already do that in Bash, but this one has a whole bunch of other ways of doing it. So I'm going to type in a hexadecimal number and it automatically works out that it's hex and we'll convert it back to decimal. So this first part of the tutorial is a bit Mickey Mouse, so we'll try and zoom through it very quickly, but I found these tools incredibly useful. So where it gets a bit more interesting is you can convert between string types to hex and vice versa, and binary numbers really easy, and this is the most useful bit I've found, because trying to sometimes work out off the top of your head what a binary number is can sometimes be a bit tricky when you're in a hurry. The reason I've put echo on the end of the line is by default. I'll show you without it. Hang on. This is going to give me, what did I type in? 0, 0, 1, 1, 2, 3, 4. There we go. So the reason I put an echo is, as you can see, it's actually just done the conversion from binary straight to an ASCII character, one character. So if you wanted to make a new line, that's just why there's an extra echo. So that feature alone was what I thought, it's cool. I can write a shell script where I've got to manipulate binary numbers and I can do it on a real simple command line. And you can see the string one there, so feel free to follow on. I guess I'll continue doing them all. rax2 minus s, hello. So I've typed in rax2, the capital S, you just give it a bunch of string and it will return you the hexadecimal form of that. And the reverse in lowercase. I'm not going to type in the whole lot, but you're participating, you can do that. So go. Does anyone need to pause on that slide for a second? Sure. Good. The next tool is called rabin2 or rabin2. It's, I guess, a bit like binutils objdump, but it does report various types of similar and different information about binary programs. I'm using /vim Linux just because I can, but feel free to put any program there and just see what it reports. Because it's VM Linux, I have to do it with sudo, so you may choose just to pick another user space program, any binary, and try it. Should have done that earlier. And I've struck a snafu. That worked earlier. Let's try this. Oh no, what have I done? All right, moving on. You can see the output that I'm expecting there, so if it works for you, that's even better. The second one, when it runs, it prints out a whole bunch of strings that it searches for in segments in the binary file. So the next one is RASM2, which lets you assemble and disassemble a single assembly instruction from the command line. Now, I'll point out with radare 2, it has quite a good coverage of a whole bunch of processors, including some interesting ones like, and old and venerable ones like the 6502, but support varies. Some it can only disassemble, some it can only assemble. The main ones like x86, obviously you can do everything. It's a worldwide open source project, so like most open source projects, people contribute what they're familiar with or what they're interested in. So the first one, I'm going RASM2, mine is AX86, says it's x86 assembler. The quotes are important. If you don't put them in, it will not work. And what it's produced there is the binary assembler code for that assembler instruction. People that are disassembling malware will probably potentially put this sort of thing in a shell script if they're trying to work out what's going on, and they might want to do 4 bytes of random code at a time. It's also handy if you're studying, and what was the code for that again, or if you're working on what's a microcontroller that you still have to write assembler for? PIC, I guess, would be a good one. You type in the numbers and see what it comes up with. And we have the reverse, so we'll disassemble. The minus B32 says it forces it to be 32-bit. B8F. B8E. Sorry? B8. Did I type it in wrong? B8. Oh, okay. It's produced something. Oh, that doesn't matter because, yeah, it's just a different register. So you can see it's produced a single line of assembly from that binary hex. So. Oh, yes, we'll get to that later. Yes, there's, yeah. Actually, that's a good question. There's a config file for the main radare 2. I'm not sure whether it goes into this, so you just have to experiment. Again, these are like, the bit I'm going through at the moment are like Unixy tools where you run them in a shell script, so you might not bother, but there was a bug where if you, which one am I doing? Didn't type in a number, but like just typed in a string, it would actually silently work, silently fail, but that's been fixed. So if you get the older version out of probably the Android one if it hasn't been patched, or off of Ubuntu or Debian, it may have that bug in it. So previously the line on the screen would have silently failed, which is interesting if you've got FFs and if you've got the 0x, and then you get completely different stuff. So the next one is called radiff, which is a binary diffing tool. There's already CMP in Unix, but this one adds some extra functionality that's useful for a reverse engineering context. I'm demonstrating this one with a shell script because what I do is I'm going to generate a random file and then change some data in it and to illustrate the diffing tool. So you can run that and then look at the source code. So if I just run it first, oops, this assumes you're sitting in the top root of the clone of the tutorial repository if you're following along. And then I'll bring up the code for that. Oops, do it that way. Gedit. Let's see how that goes. If anyone knows why gedit is so slow when it's just a text editor, I'd love to know. So it's a fairly simple example. I've just generated a random file. By the way, this one may fail. I know it creates the temp directory now, so that's good. So it basically just makes a couple of random files. So you can see on the, probably you can't see that. If you look at the output, and I've got changing 4 bytes, I've changed 4 bytes in one file, and so the binary differ has picked up one line, and then I change 4 bytes and it finds them again. So it's a very simple example, but CMP has a minus B, which tells you the byte number and some other stuff. But one of the good things about, oh, the other one. RARDIF is it can do some other interesting features. In this case, this example, what it actually attempts to do is find code similarity, which is different from just the raw binary. So it will interpret an ELF file, which is a Linux binary, for example, and try and show you where in the program there might be differences in the code, so which is different from just raw data, which if you're looking to compare, say, two versions of software which are similar but you don't have the source code for either, it can give you an idea of how significant the change in the file is. So again, if I run the example, the programs in this example of the C source code is all present as well as the binaries in the GitHub. So if you're interested in how I made them, they're just a couple of Mickey Mouse programs, but you can look at that and try it yourself later. And that's, I've forgotten the command line option, so let's try that. There we go. You notice the slide, I chopped half of it off just to make it fit, so there's a bit more in the software. So actually I will bring up the C for this just to make it more obvious. So in this particular case, what I did, it's a C program that just munges a couple of numbers and does a loop, and one of them prints something different from the other. And I controlled that with an ifdev when I built it. And the bit of different, I keep putting my finger out. So you can see the bit of the ifdev where the case statement is that unmatch in main. So that's why the diff program is telling you that. So that can be handy if you're trying to see what's happened. There's a sort of an ongoing problem in software to do with provability that a lot of the crypto people were interested in, where how do you repeatedly build a piece of software to be identical every time so that you can make sure that someone hasn't changed something on you without you knowing. So being able to search for differences is a useful thing. RAFind2 is a binary search tool. So in the example repository, I've grabbed just the standard OpenWRT Linux image and dropped it in there just to demonstrate. And normal diff searches, normally you can grep a text file. Grepping binary is, well, it's binary, so it doesn't work that well. So this is like a grep for binary files. So if I go... So that file that it's doing is in the data directory, if I spell it right. Yeah, that one. Oops, what did I forget? So the string goes there. And what's really useful about that is it prints the hexadecimal decoding as well as the string it finds plus the nearby bytes. Now, one thing I'll say with all the programs I've looked at so far and all the rest of them, if you go RAFind2 mine, the help is actually pretty good. All of these programs have a lot of options, way too many to cover in here. So if you wonder, can it do this? Just have a look and try it. It's an awesome program to experiment with. So those are some of the tools that come with radare2. Just by themselves, they're useful. But the main reason we're here is to have a look at radare2 itself. So if you're familiar with IDA, it is designed to do similar stuff. It doesn't yet have a fancy GUI, but I'm sure the people that build it would love someone to come along and write one. There is a web GUI which has just come up, and it's in beta, so it's a bit buggy, but we'll have a very, very brief look at that later. Sorry? Oh, there is one. Okay, awesome.
It's not by Radare, guys.
Oh, okay. Yeah, so apparently there is a GUI that someone else wrote that didn't write radare, that wrote a GUI for radare. But this is cool. We can all learn from each other here. I love this place. So I did an example here just to use sbin inits. You don't have to use that. You could pick a different binary. This is just to demonstrate some of the things you can do with radare2, some of the simplest bits, and just get a feel for how it works. So to run it, you just type radare2. Now, when you run it, I'm just going to do it that way for the moment, you get a prompt with an address. If you hadn't typed in that config file that I showed at the start, there would have been a fortune cookie in between there, which most of the time gives you useful information about the program. So the usual way you run it is you give it a program name. And if it's a binary that's ELF or portable executable, if you're looking at Windows or various others, it will actually detect that and understand it. Or you can give it an option to look at a raw binary. What it does is the number on the prompt is the address of the starting entry point for the binary if it's not a raw binary. The prompt is in colour, which is incredibly useful, but if you don't like that, you can go into the config to turn it off, and we'll take a brief look at where you find that later. Every command in radare has help. All the commands are based on single letter commands, so it's a bit succinct, but it's designed to also be scriptable, which it's a Unixy type program. So any letter I'll start with the first one. If you just go question mark, it shows you all the commands, and if you give it a command and a question mark, it shows you the variants of that command. There is never a space before the question mark if you want the help. Some of them, if you put in a space and use a question mark, it will interpret it as a string or whatever, and you'll not get what you expect. So next one. So let's get into some actual disassembly. So I've loaded a program, in this case it happens to be the init on my laptop. PD, P for print, D for disassemble, and then question mark shows you different ways you can disassemble. PD32. So what that's saying is just give me a disassembly from the current address into the program for 32 instructions. And I always get this backwards. Yes, 32 instructions. Awesome. And it's given you a colorized disassembly, which is incredibly useful because you often want to find stuff in a hurry, and if you're like me, unfortunately it's often late at night too. So I find this works best on a black background, but again you can change the colours when we get to that later. You can see at the top under the PD32 it's auto-detected certain labels out of the software. So entry 0 is the entry point for a ELF binary, which is a Linux binary. x86 is one of the ones that does this best at. So you can see on the right hand side it's worked out that the memory address in that assembly instruction is pointing to what could be a string. It might not be, but it does its best to guess like how the strings commands works in Unix. And down here on the bottom, it's worked out there's a branch. So with the x86 assembly, if you not familiar with it, there's a jump instruction after the comparison. The jump is a jump if it's greater than or less than or whatever you need to do. And it actually gives you a call graph. Now this is one of the most useful things about this that you're not going to get if you're using, say, objdump to just do an disassembly. One of the next cool things about radare is it can do inline math on instructions when you're navigating around. I probably should have split this one. So for navigation, the main command you use is S, seek. So you're seeking to different addresses in the binary or in the memory you're looking at. So the first thing I'm going to do is I'm just going to jump forward 100 bytes. So, and then if I go PD32, again it's now disassembling from 100 bytes further down from before. And you can see, if I move the mouse, maybe I should do it that way, that would be better. So where the mouse is, you can see the pointer was previously at 804A, whatever it was, it's now 100 bytes. Right. It's in approximately 100 bytes because the assembler instructions are different lengths. And if you remember when we looked at RAX2 and it would just automatically detect different types of numbers and convert between them, the same functionality is all built in here because all these programs use a similar back-end library. So if I go X10, it's the same as if I want 16 instructions. And that can be incredibly handy because it saves you sometimes having to convert in your head if you've got a number in one format or another. The other thing is it will pull labels out of ELF binaries or portable executables if they are present. So most of them go into a symbol space. So I can go sim dot underscore init. And that's actually seeks the address to the underscore init function that's in that binary. And then I can...
It also do tab completion of those names too.
Awesome. So you can do tab, so you've confirmed that tab completion works. That's great. I'm still finding my way. There's so many features in this program. So what you're getting today is a lot of what I've found useful. So P capital D will actually do it in bytes instead of in assembly instructions. So they've thought of everything because, again, you want to run this stuff from a script a lot of the time. And if you can have as much variety in how you use it, flexibility, it's a really useful tool. The next command I'm going to run will look for function analysis. So what it will do is we're sitting at init. AF will analyse that function, and if you go PDF instead of PD, it will print to just the end of that function instead of 32 or 100 or the default number of bytes and instructions. And you can see now, again I'll use the mouse rather than trying to turn around and point, that blue line on the outside is where the analyzer has detected that that is the length of the function. So it's able to look for, say, a return instruction and other similar constructs and work out that that's what it thinks the function is. It's not always right, because if people code in raw assembler instead of from C or another language, they can do all sorts of tricks that can violate some of the common ways this works, but most of the time that will work. So where was I? And as I was saying before, you can actually put inline math in those in the commands as you use them, which can be very handy as well. So plus. So in theory, that will jump me a bit under 384 bytes, or not. Let's try again. Yes, so that is approximately whatever that adds up to further down. So, which is very useful if you're writing a script to this stuff. Another important feature is you can edit data or modify data or code. So it's like a generic binary editing tool. So what I'm going to do is, as well as files, it understands special URLs. So a malloc one says, just give me this many bytes of free memory to play with as a virtual file. If you just go radare 2 minus, it gives you 512 bytes by default. So in this case, I'm saying, just give me 32 bytes. It's addressed automatically from 0. And what I can do then is directly assemble into that memory. So what I'm doing first is, if anyone recognises this, I'm telling it that the next bytes are going to be in something called 6502 assembly. If you've ever watched... sorry? No, not it's in Terminator 2, is it? Okay. I was thinking of the cartoon, which has there's a robot called Bender, and that's the one, yes, Futurama. And so his brain has a 6502, but so does Apple II's, and Commodore 64 has a variant. So I thought, for old time's sake, we'll have a go at that. So this is where the tutorial gets slightly annoying, because I've got to type all this in now. But 8D00. Actually, I'm going to skip this, because if I just write that to a file, I've actually got a script that does this in a minute, and I'll show you that instead. So, but feel free to copy and paste it. No, you probably can't, because I haven't uploaded the slides yet. If I disassemble where I just went, you can see I've typed in the A9018D0002 is those first two assembly instructions. So we've basically assembled some raw code into this memory map, and we can write that out to just a junk file or whatever we feel like, which is the W command. So again, if you want to find out what options all these commands have, just use the question mark. So I've saved that one to disk. So in the examples directory, there is a program called, where is it? Bender. There you go. So, which is the robot's name. And that does the example I just showed. So if you wanted to see the complete we can actually run that script and get the actual output. There you go. So instead of typing all that in, I've scripted it. So there's an example of how to script it, and we'll look at that a bit more in a minute. And the second example on the screen is the opposite operation. I'm assembling assembly language instead of binary assembly. I'm assembling opcode instructions instead of the raw binary numbers for the assembler. So radar 2 minus A. This time I'm using x86, but I'm going to use 16-bit x86, which is what was around on DOS computers before we moved up to more modern chips. This is just a simple hello world example. What you can do is, in about the same number of instructions, format someone's hard drive from DOS. So luckily we're running Linux and I haven't put any accidental typos, so you're not going to just blow anything up. You can get DOSBox and FreeDOS and various other programs that you can run emulators inside Linux or on Android or whatever. And you can find your old DOS games and play them, which is quite interesting. So now, in this case, I've got quotes around it because of all the spaces. So I'm going to go WA. Oops.
Can you leave a slide up on the screen?
Sorry.
Can you leave a slide up on the screen for 30 seconds?
Yep. They will be afterwards. Yes, I've got to upload them to the. Yeah. I probably could actually. I'm going to cut and paste from, see, then I've got to find it in there and it'll get all messed up. So that's a good idea. I'll have to remember that if there's a next time. Yeah, so basically, I can walk through that. It's, printing a string and exit as was pointed out. So if you were to do all that, you would see, actually, you won't actually see anything on the screen because it's going to give you a program on disk that if you ran it on a DOS computer would do that. So I just use that as a very simple and interesting example. Am I right to move on for this screen, or are people still looking at it? Yeah. Okay. So, and in any case, here we go. This is another scripting example. So that's one of the big things I'm trying to demonstrate with this, is it's really useful for scripting this tool. So, actually, I'll stay there a second. So there are multiple ways to skin a cat, as with a lot of Unixy type programs. So the first one, I'm specifying on the command line that there will be a script that will be using x86 assembly and 16-bit mode, and it will be opening a file in write mode to save it. As was pointed out earlier, there is a configuration file, which I'll get to as well, where you can change some of the defaults. The second example has no options on the command line other than saying run this script. And inside that script, it sets the same stuff. So there's different ways to do it depending on however you're building up what you need to work on. So I'll just run the second one just to... They both do exactly the same thing, so I was just going to run the second one to keep moving for everybody. But the cool thing with this is you can encourage you to try other commands on the command line that are similar to what I'm doing with your own numbers or binaries. And then I'll be taking a session explicitly for questions in a bit if you come across any problems doing that. Mine is where am I? Examples. DOS. So, whoops, what did I miss? Double minors. So if you don't give any file name to radar 2, it complains. So double minors means I'm not actually specifying a file name, it's actually going to be set in the script. So I'll open that script up in a sec. So that's a perfect example of how you use this in a script. The entire script does all the work and produces some output that you could potentially pipe into somewhere else. And it saved me typing all that in. So you can see it's generated the bytes for that data. Keep pointing. You can see near the mouse it's generated the data and written it out to a file. And then I've run a second thing I'll show you if I go back to the screen. Oh, actually, I'll get the script up. So, gedit. DOS. So this is what we just ran, so I'll walk through it. The only difference from the first one, which I haven't bothered to run, is that it doesn't have the E in the first one because that's done on the command line instead. So where it's going E is it's specifying a configuration variable, and I'll talk about that on another slide in a minute. But it's setting x86 16-bit mode. It's using the O command to open a new file that we're going to write to. We then assemble to the seek pointer, which we went through before, those instructions. Skip forward 20 to 32 bytes, and then we write into the same binary the string hello world. So that 20 there near the caret is the address that we've seeked to where that's going to go. So it's a bit of a hardcore way to assemble some code, but it demonstrates the example. And PX is printing the hex dump that you saw in the colour. So if I go back to there, and there's the result on the screen from running that example. So the next really useful thing that I've discovered with this software is shell interaction. So all the commands that are built into it, you can send to a pipe, or you can grab input from somewhere else and integrate that, which is what makes this so powerful where I've used it, found it useful. So in the first example, I'm going to go back to the one I did before, which was just look at a binary. PD dump the default number of bytes, which is like 256, I think, off the top of my head, or the default number of instructions. It's piping it. After the pipe, I've just got a plain old Unix command, word count, WC-L, will tell me how many lines were in that disassembly. So if I was to run that without it and manually count it, there's 68. Now that's an approximation because, as you can see near the mouse, it's putting references to various other parts of the binary file. But you can turn those, you can tweak that output with some of the configuration options, and if you needed to get an accurate count, to do that. And this is quite an interesting one because you can see there's a few spots in here where it's doing jumps that it's detected. The second one, I'm not going to run that because that script doesn't actually exist. I just did it to tell you about it. You can, the backticks, like in the Unix shell script, you can run a command and grab the result, say if it's a number or something, and pass it into a radare command. And the third one, hopefully, is reasonably obvious. I can send the output to just some file. And then the fourth one, the bang, will run a arbitrary shell command to do something with that. So I can actually go cat there. And I get the same thing but not in colour, obviously, because all it does is run cat. So as you can see, that's quite handy if you are in, say, a tight terminal because you've installed this on an Android or something. You don't have to go out to another shell to actually run a command. F is a flag command in radare, so it's to do with manipulating those symbols that we saw before. And I just use that in this case just to show you that I can use less if there's a lot of data to page it. Of course, the downside of paging through less is you lose colour, at least in the default. And the last one, no prizes for guessing where 42 comes from. It's the life, the universe and everything. But so I'm basically saying disassemble 42 bytes, but in this case it's actually getting 42 from running a shell command. So I'm not going to work through this one. I've just provided it as an example that you may choose to do in your own time because I don't want to be responsible for someone destroying their partition sector. So basically I'm using radare 2 there. I've run it with no program at all, and then I've opened up a device under Unix or Linux, and I've dumped 512 bytes, which is the boot sector of a, well, until a couple of years ago, nearly every computer that was running x86. And then I'm disassembling the boot sector code. So yes, that's the kind of thing that this tool can be quite handy for if you, like me, like playing with old computers and you're trying to work out what's going on. So I've mentioned this a few times. Radare has a pretty good configuration interface. So the E command is the access to a lot of that. So if I go E double question mark, there's a great big list of options that configure things like colour, how wide the screen is, and fine-tuning for the analyzer that looks for functions and calls, prefixes and various other information. And you saw a couple in one of the scripts I did already where, for example, it sets the number of bits. So x86 you can do 16, 32 or 64 disassembly. The architecture, which changes the the CPU architecture and so on. So it's got help there. And there's an example there. If I do a disassembly, and then I go E as in line width, lines width. I might do a big one so that it's really obvious that something happened. That's just changed the indent to the left. So if you're looking at something that's quite a complicated function, which has a lot of these call graph sections, you might want to shift it across so you can see them more clearly. And if you remember back at the start, I got you to make a config file. You can save all of those E commands or any command in there and have them run automatically every time you run it if you have a particular preference for colors or whichever other configuration you need. The next command I'm showing here is I, which shows you information on the currently accessed file, which if it's an ELF or a PE, it will dump various metadata about the file you're looking at. And I'm going to run IS, so that will show me a whole bunch of symbols that it's detected out of that file. And that's just repeating what I just said. So I guess there's homework if you're looking at this afterwards or you're doing it while I'm talking about other things later. You can tweak a disassembly layout, so look at the script, look at the E question mark and see what you can fiddle with. And I believe there's one that lets you retain your history for when you restart it. So you can go up arrow like in GDB or whatever and see commands you've run in a previous session. Yep.
So those symbols, they just pulled that out of the ELF binary?
Yeah, hang on, go back.
Previous symbols that you just showed?
Yes.
Right.
Yeah. So if you've got a binary with callbacks or debug information in it, it uses that where it can. The other thing is you can set your own symbol names on addresses. I'm not going to cover too much of that today because we don't have enough time. But yeah, it's very useful. So, was that the same slide twice? Interesting. There's a bug in my presentation. So this is one of them where it starts to get interesting. If you've used IDA, one of the main things about that is you can do graphical call graphs. So radare 2 will do that as best it can as well. So I'm going to open up this time I think that one that says temp should actually say examples. So if I go radare 2 examples slash, similar one. Yeah, so that slide has a bug. And then I go AA. What it will attempt to do is analyse as much of it as it can and find all function calls that are in there, including ones that aren't labelled, if there are any. And then I go AFL. It will list all the functions that it can find. And you'll notice some of them are just FCN dot. So what it does is it thinks it's found a function at that address, so it doesn't know its name, so it's just given it a label. And what you can do is rename that if you need to, which comes in really handy when you're trying to understand some code that doesn't have symbols in it. And then what I'm going to do is I'm going to run a command called AG, which generates something called a dot file. So it uses a program called GraphViz to generate the graphics. So one good thing about this is it leverages existing libraries to do useful things. And I'm not going to run that without the redirection to a file because it will produce a fair bit of output. I'm just going to call it that. And then using the function I showed you before where then you can run a program straight from the shell, I'll use x dot if you have that available, and then the name. And, oh no, I had that there yesterday. What's going on? Oh. Okay, I'm just going to have to wing that one. So luckily, there is a hard to see. If you've got x dot, you'll get a much better picture of a snapshot. The first example I've just run actually has a really wide and very hard to see, and you've got to zoom right in because it graphs everything it finds in the file, including even random functions that the linker left in there for whatever reason. So the second example I'm going to run, it's actually giving it the function name. And I wonder if this is a buggy. I did test this bit, so I don't know what's happened to my computer. I reckon apt-get has gone and taken something back off that I had, which is nasty. But anyway, when you run this second command, you actually get the output that's really hard to see on this slide. But if you're running it on your own screen, you'll see it up close. And so the big one is actually main, and then there's another function coming off it. And what you can do, if you're interested, again, the source code is there. You can look at it and see how the call graph lines up with what you did. And often, especially if you're using an optimizing compiler, things don't always match because the compiler may hide functions. And sometimes they also drop in functions called intrinsic functions. So you think you're doing math, and the compiler will actually be doing a function call rather than just raw code. And you can automate all that. As I can see on the screen, there's a sequence of commands that you could put in a shell script and run it. I suspect that may fail really badly, and if I haven't got x dot working properly. And did I put in the examples an output I can show, please? Let's see. Yes, there's a solutions directory, by the way, which is going to save my skin here because I can do this. Yeah, there we go. So this is that one that's really hard to fit on a slide, but now because I've got it up, I can zoom in. So for the benefit of people who don't have the tool in front of them. Oops. That doesn't look like the same one, but anyway, whoops. But you get the general idea. Dot files look like this. Which is a reason to not normally look inside them, but to use a tool that understands them. So yeah, if you run examples gem main callcraft, it is a script that does the code that's there and produces the same output. So I'm going to move on to strings. So what I'm doing here is, again, I'm looking at just a program, and then I'm going to do a search. So if I go radar2/sbin/init /, so it's a bit Vimish or VI-ish. Awesome. Oops, where am I? We'll search the program that's just loaded and look for that string. For some reason, my version that I'm running on this laptop has it one less than when I did it on my 64-bit laptop, so that's interesting. So then I can go print a string. So the address for that one is at... Now this is where you've got to be a bit careful, because some of the instructions require you to put the @ symbol when you're referring to an address. So remember that if things work a bit strange, you've probably dropped an @ So 08048F3B, just to illustrate. And that's a string that happens to be at that point in memory. So if I go PS question mark, and it can print out different types of strings. So if you're dealing with, say, looking at a Delphi program, which is Pascal half the time, you can actually, say, print a Pascal string, or if you know it's got a 0 terminator. Occasionally you might do something accidental like this, or sim.main. Oh, come on. And it will say, it'll give you that warning, which is actually better, because most of the time it says, pops up a message and it says, do you want to print out 465,000 bytes? And you kind of go no, because it can play havoc with your terminal. The other thing is the search actually generated a temporary label, so I can always do it this way. Call it lost it. Hit 0_0. Which is a bit more convenient than having to sit there and read the address and then type it back in. And the last one is I'm doing a hex dump at that same place. So what I'm actually going to do is seek. So I'm going to change the pointer from where I'm currently actually pointing at assembly code to pointing to data code. So pointing into the data space. So depending on your laptop, the numbers will probably vary in your case, because each computer, each operating system spin everything's up in a different address, or if your computer is smart enough to use address space layout randomization, they may be different every time you run. Actually, they won't be, because you're not running it, we're just examining it, so that was a silly thing to say. If I go px, so you'll notice I've done the ps command to the address where the string is, and I've done, that should have said s, not ps. It's now changed the address to, what's going on? There we go. Did I have that? Yeah, there's a typo on the slide there. There should be no @ on the S command. As I say, it's a bit confusing. For some reason, some commands you need an @ when you do an address, usually the print ones. But so I've jumped the pointer from what was assembly to what was data. If I try and disassemble that, it gives me junk. But if I do a hex dump, PXL. So that's actually an L, PXL. It's going to give me, and the 1 says do 1 line, so I could go 10 and get a hex dump of whatever's in memory for 10 lines at that point. And I'm going to run the analyzer again. Now it has this concept of flag spaces, so the default one has function name symbols that's pulled out of the ELF, but it has a second one where it tries to detect strings. So if I go FS, it says switch flag space to strings. And now if I go F to print the flags, what it's actually done is it's found all the strings in the binary and it's generated a label for them that sort of matches the ASCII, but it does safeness, so if it had binary Unicode things in it, it should put an underscore, I think. I haven't played with that enough to check because everything I've disassembled didn't have that problem. And then I can go F, grep R limit, and we'll see how many times it found a string with that in it, and that example has just failed on me, which is interesting. So, and PD1, whoops, PD1, come on. Yeah, junk because it's a string. Yeah. Okay. What I was expecting to happen there is maybe that's because I've used the hit. When I tested that before, what's supposed to happen is if it's got that's right, a label. So if I was to seek, if I go back to the strings and I pick one, say str.once, and then I go s at str.once, and then I disassemble that, it actually shows you what you might see in an assemble program when you've got a data specification in the assembly. We briefly touched on this before, so I might just skip through this a bit quickly. So it accepts a URL for memory. The minus sign is a default, give you 512 bytes. The minus W means that you're able to write to that file. So if you don't specify that without taking explicit commands, you can't accidentally clobber something. The last one, you can specify a different offset for the ELF from the default. Or if it's a raw binary and you don't know what it is, but you happen to know where the bootloader is going to load it, you can force it to override that. And I don't have a file called bootloader bin to demonstrate that with me, but when I was working on the gadget I showed you before, that was how I was looking at it, because I knew the kernel, the bootloader was trying to load it to that address, and I wanted it to try and match it in radare. And there's some other features that I don't have time to go through. There's a text mode UI, which is a sort of a GUI with a more interactive way than having to remember some of the commands. There is a web interface, which I will jump into just very briefly. No, what have I done wrong there? Oops. That's the TUI. Nothing wrong. Okay, I've got a typo going on there, or I've stuffed something up, but there is a beta. There's a clipboard, so what you can do is yank data out of memory and then paste it somewhere else, or use it in a macro, which is another facility, which is quite handy if you want to automate stuff, and so on. And there's also $ variables, which are similar to the configuration but used for querying information. Now, if we get time at the end, which we may not, so I've got this as a homework challenge. In the Git repository is an Arduino binary. The whole solution I've listed there, but it shows how you can use radare and tools for parsing various binary formats to take a program and then modify it and try and find out how it works, along with a technique for doing that. So Arduinos have hex files. So there's a program called srecord that obj copy to convert it out to binary so we can look at it in radare. And then there's another program called srecord that we use afterwards, after using radare to modify it, to turn it back. Perhaps, and also if you, for example, knew all about MIPS already, which is what I'm going to talk about next, you might choose to work on that now. So I'll put questions if anybody has any. Yep. Oh, were we running the mic?
Hi, I'm one of the people who came in through the door late and annoyed you.
Right.
Could you please let us know where I can get the examples?
Yes, the Git repository there's a wiki page on the conference wiki under tutorials, and it's all listed there, so you can just git clone it. So the instructions are all online. I will be, they want me to post the slides somewhere. I'm going to upload them to my website, but they'll be eventually on the conference somewhere too. So.
The switch for web interface is dash lowercase c equals capital H.
Oh, okay. So,
It's in the, when you run it.
yep.
At the beginning, dash lowercase c equals capital H. Lowercase c equals.
I'm not sure why I'm having to do that here, because when I've got it built on my desktop computer, it uses that W command, so obviously something's changed. So I guess, yeah, so if you open that in a browser, whoops, where am I? Ah, that's a good trick. Wrong browser. Oh, actually, I can probably just go do that. And if we get really lucky, this is actually Conqueror, so it may not work that well because I've only tried it in Firefox, but yeah. Because it's a modern web GUI, it doesn't understand it. So how about I just, yeah, so, and this is a beta, so it doesn't quite work, but when it's finished, I think this is going to be absolutely awesome because it's a lot easier than having to remember all those commands. So you can see you've got your color-coded disassembly and you can click on things and browse to it if the JSON was working, but this is the wrong browser, so I'm not going to demonstrate that. Anybody else? Yep.
Yeah, this is a question you might choose not to answer, but I understand the way OpenWRT got started off was they could prove that the router that they started with in fact used free software. So they demanded copies of the source under GPL. Did you think of doing that with the thing you started with?
Oh, no, there's actually, okay. If you're referring to the one I've got,
Yeah.
they've actually released the GPL software for it, but there was no information on how to get into it and do it. And I had to work out how to get into the bootloader because it wasn't U-boot. So that's why I disassembled it. So, but yeah, I think you're correct. I've only found OpenWRT about 3 years ago. But yeah, there have been all sorts of issues with embedded software and people using BusyBox and other programs and not actually doing what they're supposed to do. Anyone else? I might as well keep going. Oh, sorry. Yep. So we'll try that. So I'm just going to talk about a few things that are relevant to where you might use this tool or why. There's traditional microcontrollers, which, you know, Arduino is probably one of the most topical ones for this conference, but, you know, it goes all the way back to 8051 and ARMS and PICs and all the rest. They will generally be running bare metal, so there's no operating system. So you don't get the benefit of a binary file like an ELF that gives you some labels, so you're really working down at the bare metal for those. And the other type is embedded Linux capable systems. As an example, the gadget I've pulled apart here. The one on the screen is called a Carambola, which is an open sourced gadget you can buy from a company in Europe. I paid about 30 euros for one. And Raspberry Pi is another one that's the same sort of class. And these all run Linux. So one particular chipset that's common on these is called the MIPS, which is actually an architecture that's been around for quite a long time. For a bit of trivia, the original PlayStation and some of the Nintendos actually ran a MIPS processor, and there was the SGI was a well-known, yeah, the Indie was well-known rather a while ago now. So Linux runs on MIPS, and basically a large number of the cheapest end home routers and gadgets like this, the TP-Links and the D-Link and all of those all run MIPS system on chips. So if you happen to be wanting to get into a MIPS device like the one that I showed you earlier, you need to know a bit about the architecture to understand it, because many people are familiar with, say, x86, and then you go look at a MIPS computer and you're like me, the first time you do it, you get really confused for a long time until you actually decide you should go read the manual and find out how it really works. So they have a pipelined architecture, so to make it more performance efficient, different instructions will be in different parts of the computer at the same time, so that it can run different parts of the decoding and execution and memory access concurrently. What that means is that you can get some interesting optimizations that make your life difficult with disassembly, and that's why I'm pointing this out, so I'll get to that in a second. MIPS has a large number of registers, and they can be used for various things. There's conventional usages which compilers will follow, so there's an A0 to A3 use holding addresses, T0 to T9. One thing that gets interesting with MIPS, if you've got to disassemble it, is different places sometimes call registers different names. So you might be looking at someone else's disassembly and it doesn't look like yours. And different disassemblers will sometimes shorten two instructions into one as a convenience, which can also make it confusing. So I'm just going to jump to a MIPS program with radare just to show you the difference. And that again should not say temp, it should say examples. MIPS, hello. So this is an ELF MIPS binary that I built with an OpenWRT toolchain. FS symbols, let's hope this works, yep. sim.main. AF PDF. So this is MIPS disassembler. That's the easiest. I keep going to point and it's not going to work. It's like any other disassembler, it's got its own instructions. One interesting difference with x86, every instruction shown here is all 32 bits exactly. So you don't have to worry about alignment, it's all forced into alignment. As an example, the first instruction there is it's adding two numbers together. So if I go back to the slide, I said it's got the destination register on the left and the source on the right. So it's saying stack pointer minus 28 hex bytes back into the stack pointer. So this has come from C. So now this is where it starts getting interesting. When you're reverse engineering, you're generally looking at code most of the time that's probably come from a compiler like C, which gives you a bit of an advantage because there will be common patterns that you can look for. So, and the same with x86 and anything else. So a very common pattern is if you have any temporary or automatic variables or stack variables as they're known in a C program, you can generally see at the start of a function that it will be saving space on the stack equal to the number of bytes taken by that variable. And often that can be quite useful information because it gives you a key as to how much data the function might be using locally, for example. So I was mentioning before the pipeline, which is one of the key performance advantages MIPS has in certain situations. Delayed branches. This cost me a couple of really annoying late nights till I worked out what was going on because I had this bootloader, I had no idea what it was doing. And I knew roughly what it was doing because it sort of made sense, and then you would have an assembly instruction and it didn't make sense anymore. And so what happens is two instructions at once will get loaded into the CPU, and even if you have a jump, they will both get executed. So you can see where I'm pointing with the arrow there. There's a jump instruction followed by a piece of assembly, and what actually happens is it reads them both, it does this, and then it does the jump, and that's to do with the pipeline. And if you have a conditional branch, the same thing happens. So you'll generally find that if, say, this was a syscall, a system call in a Linux program, after the jump is actually one of the arguments for the system call. So where I was getting into trouble is I found a function that would print inside this bootloader, but half the time what I thought was the string argument was rubbish, and then I realised the instruction afterwards had a pointer that matched the string when I did a string search. And that's when I went away and read the manual and learned about all this, because I'd come from an x86 6502 style world where you don't have to deal with this. Where am I? Oh, come on. That one. And again, you can see that in the output here. So there's a branch instruction, but in this case, the instruction afterwards always gets executed. So you'll sometimes end up with some strange looking code where if you read it sequentially, it looks like it's writing a value into a register and the next instruction is writing another value into the same register, which normally you wouldn't make sense. Often you'll get NOP instructions after jumps too, so the compiler or the designer realised, well, there's nothing I want to do in that slot, so I'll just have a no-op. Other things to deal with MIPS is MIPS has this concept of an instruction set extension. For various reasons, the most obvious example I've got there is a 16-bit instruction set extension, even though it's 32 bits. if that is present in the system on chip, you can write assembly code that compacts some of the instructions into 16 bits each, so you can put 2 into the 32-bit space, which is really awesome for saving memory. OpenWRT recently enabled that by default in a lot of their builds, and it's not supported by Radar 2, which it's coming. One thing I didn't mention before is Radar 2 backends a lot of its assembly, disassembly into a product called Capstone, which is another open source library for doing disassembly. And that's the bit that needs to do the MIPS work. So that's coming at some future point, but there's a lot of work to be done in various areas. So cache configuration is another interesting one, and I'll get onto that in a second. And alignment, so as you saw before, everything has to be 32-bit. So you need to just remember that all the instructions line up properly. If you're looking at MIPS, particularly if you're looking at, say, a bootloader or bare metal, you've got to pay a bit more attention to the memory map because Linux isn't there to sort of hold your hand with that. So the KSEGs are equivalent of a protected mode memory area. So once Linux is up and running, your user space program runs in KUSEG and the kernel is running in KSEG. But there's some special stuff about the KSEGs. So KSEG 1, as it says, I'll move the pointer. That is uncached. So if you have an address there, your hardware, say hex A1000 might be linked to address 0 in RAM. It will never use the cache to get to that if you address it as A1000 in your assembler. But if you go to 8000, the same data is accessed but through the CPU cache, which will give you faster access. Now what that means is then you'll generally access direct memory map registers at, say, an address beginning with B, so BF, for example. There's a whole bunch of well-defined ones in the system. So just things to be aware of if you're looking at disassembling code and wondering why you might sometimes see the same address done differently in 2 places. And the top one, KSEG 2, is designed to work with a memory management unit. So that's typically used in Linux to load the memory modules in the kernel. So getting on to a bit more interesting stuff. So you do what I do, you go get one of these boards and you want to know a bit how they work. Most of them are fairly typical embedded systems. There'll be a system on chip, so it's a CPU core plus a whole bunch of I/O. MIPS itself has various flavours of CPU. 34KC is probably one of the most current ones that are found in routers. Your typical gadget these days will have U-boot, which is an open source embedded bootloader. And then laid out in memory, you'll get the kernel usually. There may be a partition in between for storing U-boot information. The kernel and then a file system, which may be a flash file system like JFFS2, which is designed to write to flash while minimising damage. Or SquashFS, so it reads it into a RAM disk and then runs it from there. There are 2 ways that these systems can be laid out as well. So the kernel may have bundled into an init RAMFS, so you don't have to go to the effort of having a separate file system next to it, and the kernel itself loads it, or it loads the SquashFS into RAM. So there's a couple of different ways to do that. So you may or may not have binwalk on your computer. Did anyone see whether I had binwalk in the wiki instructions? Oh, good. All right. So we'll try this now. So what I've got is, as we looked at it briefly before with that rar bin command, the rar find command, is there's an OpenWRT system image in the data directory. So I'm going to, fingers crossed, run binwalk. So if I run it without an option, which isn't on the slide, but I'll do that first. Binwalk does this kind of unpacking of layers within layers, because firmware, for various reasons related to doing with memory conservation and obfuscation for many manufacturers, will have one file that you can send across the internet and download, which you then unzip and then you put into a web browser, which then gets downloaded into the firmware, and then that gets unpacked and written to the flash and so on and so forth. So binwalk will untangle this mess and tell you what you're looking at. And so you can see, if I move the mouse to it, here binwalk saying, is that system upgrade or the flash image for OpenWRT, there's a thing called a U image header, which is telling me that it's actually a Linux kernel that's designed to work with U-boot. So if we go back to the diagram on the previous page, that will be saved into the flash just after the U-boot env area. That's where that U image is designed to get copied. These are all set up to go consecutively, so sometimes there will be padding to line things up. And then the second big one there is a SquashFS file system, which is what I mentioned as well. So, did I? Yeah, we had that one. What I'm going to show you now, because there's no slide telling you to run the command, is, and this may not have quite made it into the wiki, I think. There's a program called unsquashfs. It may be in your Linux distribution or it may not. Sometimes these things are a bit hit and miss, but you can download it and compile it. And what that will undo is unpack that squashfs image so you can actually see what's inside of it. So if I go, and I've actually skipped a step there. So I'm going to run binwalk again a second time. I'm actually going to, check whether I had one sitting over. If I run it with -E, it will, instead of just telling me what's there, it will unpack all those different segments into separate files. So it's taking a bit longer this time. So what it's given me is, and it's a bit annoying with it, put stuff in the directory where the file is, even though I was in a different directory. It's made a file with starting with an underscore, and that will contain the unwrapped versions of what was in that firmware image. So if I was to run file against that one that it arcanely has called 40, and the reason for that is it names the stuff after the address within the file, and that's not going to work for me at the moment, but that's actually the kernel image. But what I was actually trying to demonstrate is the squashfs. So I'll remove that directory that I left there before, and then run unsquashfs again. So that 10e469.squashfs is, it found a squashfs file system starting at that address into the firmware image. And if I run that, I've now unpacked it and it's made a directory called squashfs root. And now you can finally see the user space that might get landed into your device out of that firmware. So you've got to go through all this muck to get to that point. Question? Oh, yep. Oh, you don't have to, but they might want you to. So. Okay, yeah, what's your question?
Just a comment. You need to be running the newest version of binwalk if it's not an OpenWRT image.
Yep.
Because manufacturers aren't nice to you. And the other thing is, the guy that wrote binwalk also wrote Sasquatch, which will detect every different variant of squashfs ever written and try and unpack it for you.
Yeah. So the comment was that to keep on top of the manufacturers, you probably need to keep getting the latest source code for binwalk and recompiling it, and same with squashfs because there are so many different versions of it. Squashfs is really, really annoying because they will run them in different endians as well. So they've got a magic number SHSQ, but sometimes it's HSHQ and various other things, and a lot of the Linux distributions will understand squashfs 3 and not squashfs 4, and it's a lot of fun. So yeah, it's good stuff. So, did I miss anything you suggested? No, good. So, yeah, I was mentioning bootloaders. U-boot is open source with usually patches to support the hardware it's running on. However, some gadgets, especially once you go back a few years before U-boot became really well known, will have other bootloaders which you often not be able to find information on, but the system is still running Linux, so you might need to go into them to find commands to be able to work out how to get Linux onto the system. So, with the gadget I showed under the, I might as well do it again, why not? So this particular one here, it had a bootloader that had some commands when you typed help, but nothing to do with getting a firmware image in and flashing it. And so I was able to use radare to reverse engineer it and look at and I found extra strings, and I thought, that's interesting, there's extra strings here, but I can't see them from help. And then I tried typing some of them in and discovered that it would let me load a Y modem image over the serial port. So that was actually quite an interesting discovery. So if I go to that, and that, and that, and that, we get back. So I've just preempted the first point on that slide. So the usual techniques for getting some firmware to try and unpack and have a look inside is find a serial port. Nearly every gadget, except for really locked down gadgets from telcos, for example, will have a serial port somewhere. They usually look like 4 little dots and you have to solder something to them before you can use them. And then you can connect a USB to serial adapter and boot the thing, and usually you'll get a terminal which you don't have to type a password in because it's just a serial port, and you've got immediate root access from the serial port so that you can look for flash. Yes?
Is there an easy way to figure out what baud rate it's using?
Is there an easy way to figure out what baud rate it's using? If you have an oscilloscope, I was taught a trick many years ago where you put the crow on it and you get it to trigger, and then you look at how wide the bits are and take a guess. Most of them will be 115,200 or 115,200 or 57,600. That's all I've ever found is one of those two. And they're pretty much always 8M1. One problem I have come across is sometimes Minicom, you've got to turn off hardware flow control before you can type into it. And when you forget that, you say, why isn't this working? Oh yes, I forgot to set the setting. Getting the firmware off can sometimes be a challenge because often custom firmwares will have various commands you might otherwise find missing. If you can get something into it, often if you've got a Linux prompt, one common technique is you find a tool chain that has the same chipset as the gadget you've got, and you cross-compile BusyBox and upload that into it, and then you've got all the other commands you've normally got. If you can't do that because there is no network, and this gadget I've got have Wi-Fi only, and then various other issues. At worst case, if you have something that can do DD, you can dump it into your terminal with logging on and then try and write a program that will turn it back into something in binary on your computer. Other techniques I've seen is if you Google OpenSSL, someone was looking at a router and the only command they had was OpenSSL, network connectivity, and they used that to actually send the data over the network to somewhere. So, provided you can type into it somehow, there's usually a way of getting stuff in and out. So one issue we've got today is you could probably do a 5-day course on all this stuff. It's a lot to cover. The radar tool has many more features than what I've looked at. Reverse engineering itself is a skill that I'm probably only at the apprentice level. I'm only playing with toys, and you go looking at what some people have posted on the internet and it's like, how do they do that? There are some techniques, and I might just jump back now to the... How much time have I got left? How much?
14 minutes.
Oh, look, good. All right. What I'm going to do is I'll jump back to what I had as the homework challenge before. So I have a binary that I made from Arduino, and then I pretended I've lost the source code, which is a reason you might want to go through this. And if I load the README and get it up on the screen, and that's not the solution. So, because I was just going to talk about techniques, that one. So what was I talking about? Oh no, I've lost my spot. What was the original question? Okay, I'll just go through it anyway. So we've got an Arduino, we've got a binary which is a hex file. So the first thing we've got is we've got this binary, we've lost the source code, someone's given us the hex file and said, oh, I crashed my computer and I've got an Arduino and I'd really like to get it back and do stuff to it. You can't get the source code back, but you can at least look at it, and if there's doing some I/O you couldn't remember, you can have a look and see what you're doing. So the obj-copy command, what that is doing is it's taking the hex file and converting it back to a raw bin file, which you can then look at in radar. And then the next command is it's saying it's an AVR binary, because Arduinos use AVRs, and then it's going to load that up and look at it in radar. And because we've got plenty of time, I'm going to attempt to do this. So we're going from prepared tutorial to sort of live demo now, so this will be interesting. So, what have I got? Radar 2. Examples. Actually, I'll cheat. So I'm not going to repeat the obj dump. I'm just going to go arduino.bin. So because it's a raw binary, it's come out and it says, oh, I'm going to start at address 0. So I'm going to just look at the first few bytes of the program. And it's a jump instruction. One technique, that's what I was going to talk about. So one technique when you've got an unknown program is you can sometimes find another program that you do have the code to that does similar stuff and compare the structures. So nearly every Arduino program is going to have a similar structure, which makes our life really easy if you're looking at Arduino instruction. So they all start with a jump somewhere else. So I'm going to go $$J. Now, I mentioned in passing before there's $sign, which lets you get information out of radar and use it in another command. So J is just jump to the address that's on the currently seeked instruction. So that's, instead of me typing 0x1E8, it's actually just going to jump to it like that. And now I'm just going to have a look at what's there. So what I would do at this point, and I don't know if I've got the output, and I don't know if there's going to be enough time to generate it. So I have, the way I would approach this problem is I had a known Arduino binary which I dumped with objdump, and I don't have it here to look at, so I'll skip that. So you have a known binary and you have that in one text editor, and then you compare it to what you're looking at in radar and look for similarities, and you think, okay, they're structured the same, so I know what that's doing, which makes your life really easy when you're trying to reverse engineer something. Oops, let's close that. Oops. So what I did in that case is I took the output from objdump and disassembled the known one and said, the code I'm looking at in radar at the moment looks similar to what I'm seeing in the program that I know what it does, and so I can guess what the functionality is. And then I was going to run AF and AFL and see what functions came up. And this is one we didn't go into earlier, so I'm going to rename. Something has not worked properly for me, which is not very nice. So, live demo. What happened when I ran this on my other computer is the function, it found a function at 07A8, which I knew from looking at the known Arduino binary was actually main. So AFN will let you rename a label to something else. So if I go AFN, actually that's what I did. So I know I'm doing now. So if I go PD again, and then A7A8 PD, let's go 300. I'm going to cheat and do this 0x7A. I think what I've done is I've not put enough information into that README. So I've seeked to 7A8, and I've realised that this is actually the equivalent of main in an Arduino program. So the current seek point is 7A8. So I'm going to go AFN main, and then that gives me a label at 7, oh that's the wrong address, 7A8. That should have been an at. So the at means go absolute as opposed to offset. There we go. No, why isn't that working? All right, I don't have time to deal with that. So AFN will name the current point to a label instead of just the address. The other thing we know about Arduino programs is they have a setup function in C and a loop in C. And again, the examples I used to repair this are all in the repository. Yep.
When you annotate with the AFN,
Yep.
can you save those between sessions? Where do those go?
There is a concept of a project that I haven't gone into where you can save information. When I was doing it though, I was being a bit more hackery and old school, and I was just copying and pasting my command history and then pasting it back again because I was trying to log what I was doing, and if I was saving it in a project, that's useful in some use cases, but when you're trying to learn what's going on, I found I'd rather repeat the things every time using copy and paste, but that was just me. So yeah, you can specify a container project like in an IDE, and it will retain that type of information. So I worked out looking at a known Arduino program where the main loop was, and then you find it in the current one, and then using radar I searched for a string, found the piece of code that was calling that string, and then I patched it to do something else. So you can read that example and try it afterwards and probably find some bugs in my solution because I've typed it up wrong. But that just gives you a bit of a flavour of what's involved in reverse engineering. It's a bit of an art as well as knowing how to use a tool. You need to think of techniques like, well, where's something similar to what I'm doing? Can I look for patterns and that sort of thing? So back to where I was, because we're probably getting close to the end now, aren't we? Yeah, okay. So we'll have a good chunk of time for questions. So yeah, it's, yep.
Are the syscalls properly recognized for MIPS?
Possibly. I've not done a lot of ELF with MIPS. I've been mainly playing with raw binaries, so you just have to check it. I would guess they would be. It'll pull out of an ELF all the labels it knows about. So if it's a function in a lib that it links to, there should be a label. I would suggest experiment.
Thank you.
Where was I up to? Yeah, so one thing we've discovered today is radare 2 is an awesome tool, but you want to use other tools for unpacking firmware and doing other things, and it's good. So you can potentially write a script that's in radare 2 that actually automates bin walking if you needed to, if you wanted to do something over and over. But yeah, other tools are often needed in reverse engineering. There's no one tool does everything because there's so many complicated edge cases and moving parts. I can't really show you a real world use case. I'm only showing you open source software that I'm disassembling because I guess there could be problems with showing non-open source software, so obviously I haven't. Radare 2 has a whole bunch of other features that are really awesome. It can be connected to GDB, so I haven't actually tried this myself, but I believe you can run a program in GDB and then spawn back and forth to radare to do various operations. It's got all sorts of features for information security, so you can hook it into fuzzing systems, use it to do something called ROP gadget searching, which is something I haven't really looked at, but it's to do with finding ways to run code on systems that try really hard to stop you running code. And it's got bindings to a whole bunch of languages, so you could write a Python program that calls radare 2 to do various things as a library. If you want something to do in the real world, it's do things like buy cheap gadgets and see if you can patch them to put your name in the web firmware or whatever else. You can have a lot of fun. The Kmart one is an interesting one. It turns out that I bought one and hooked it up to a separate network from my normal network with Wireshark running, and one of the first things it does is it goes back to a country overseas to do the dynamic DNS, which is really interesting, and I decided not to run it connected to my normal network and just use it internally. There's a really interesting example there where someone, all over the net, there are examples on blogs where people are using IDA to do stuff, so it'd be an interesting learning exercise to try and repeat what they've done in that using radare 2. If you're really, really keen, there are people who have jobs virus samples, but they take precautions like running it in a VM. I've never tried this myself, but I like reading about it lots. I let other people do that and I just read what they did and think that's really interesting. I won't repeat that one. Yes. Radare 2 is an open source project under heavy active development. They seem to be pretty friendly. They've been really patient with me. I've submitted a few patches. I think they like the fact that some of the ones I submitted were for help. It's on good GitHub. They've got a regression test suite which always needs help, and the web UI is in beta. There was a question over here. There, two, one, yep.
If you want a really cheap device to hack on, there are $9 modems on Chinese resellers. They take about a month to get here, but they're very similar to the device you were showing on the screen there.
Oh, okay, sorry.
Just want to comment on how you'd actually get hold of the firmware out of the webcam to play with it.
It just runs Linux. Yeah. So I hold it up a serial port, jumped in. It runs U-boot, so I was able to use U-boot to just copy it off. So, and then I bricked it, and I've been too busy to fix it. Yeah. So most of them, yeah, it's all serial port is how you get in. If you're interested in going further, CMIPS Run is a book on O'Reilly. Wait till they have a 50% off and then buy it because it's quite expensive, but it is got a ton of information about how all the MIPS pipelining and all the other stuff works. Radare 2 has an online book which is really, really useful. And there's a general reverse engineering website that I came across just the other day, so I thought I'd put that up there for people to look at. And there's any number of people love pulling things apart and then blogging about it and showing you how I did it. Hackaday website. And thank you very much. And I guess if there's any more questions, we'll do that now. Yep. Yep. Oh, yeah, so what Darryl was saying is often some of the gadgets will have a JTAG port. Actually, there's one on there too. So even if your serial port is causing you problems, if you're into hardware stuff and you know what you're doing, you can get a JTAG reader. Does this have a zoom? Oh, it doesn't matter, I'll just move it up. Yeah, so that row of pins there is a JTAG connector, so you can solder that up and hook it up to a JTAG thing and use that. Someone earlier mentioned when OpenWRT first started, it's actually named after the routers that Linksys had. There's a WRT54G and similar ones. I had one once and I bricked it, and then I discovered that I could get a parallel port and a chip and a couple of resistors, and downloaded some software that hooked up to that same JTAG pins in that, and it took about 4 hours over the parallel port, and then I had my flashback and I unbricked it. So there's a lot of, all this stuff's all documented all over the internet. It's like just a matter of knowing what to Google for half the time. So anything else? I'm good. Thank you very much.
So on behalf of the LTA team, you've probably all been to lots of presentations. Here is a small gift from everyone saying thank you for putting on an awesome presentation.
Yes.
That's the word.
Thank you very much. Thank you.